So everybody is ready. I think we are late. So I'm Axel Röbel, and I have been asked to be the president of this defense. And my first task is to introduce the committee. We have Emilia Gómez from here. I think everybody knows her. And we have Mauch from the University of Queen Mary. So I'm Axel Röbel from IRCAM. So for the evolution of this, or the déroulement, I'm too much into French language. The evolution of this presentation, you have 45 to 60 minutes to present your work, and then we will have about 40 to 60 minutes again for the discussion. And then we will decide as in the committee secretly what we think about your work, and then we will announce the results. So I think we should start, and we have been asked to go there because we can see better. You and your presentation.
So, hello everyone. Can you hear me well? First of all, thank you for being here, present, inside, given that there is such beautiful weather outside. Today, I'm going to present the work done as part of the thesis titled Knowledge-Based Probabilistic Modeling for Tracking Lyrics in Music Audio Signals. This has been carried out under the supervision of Dr. Xavier Serra, and I would also like to thank the jury members for taking out of their time for reviewing the thesis document and for being present here today. Before we start, I would really like to thank to some people that have collaborated and contributed to this thesis. First of all, I would like to especially thank Dr. Xavier Serra for giving me the opportunity to be in this project, to accomplish this thesis, and for supporting me throughout this long scientific journey. Then I would like to thank the numerous co-authors and collaborators, some of which are here. And let's first look at the title. By modeling, we mean several different computational models. We prefer probabilistic models because they can handle the temporal variability of music, and especially singing voice. By tracking lyrics, we will focus on tracking the progression of sung lyrics in time compared to written lyrics. Whereas the model is theoretical and capable to be applied for any task, one particular good example where it can be applied is the task of automatically aligning between written lyrics and audio. We will focus on a model that is knowledge-based, where by knowledge we mean knowledge of events that happen in the music simultaneously to the sung lyrics. And by music audio signals, we mean recordings of music. Additionally, a big emphasis of this work is on reproducible and open research. Therefore, all the code is open under GPL license, and the data is publicly available. You can find all the accompanying materials of this thesis on this page. And we consider that this is important to encourage the reproducibility of this not so much studied topic. The talk of today will be divided into the following sections. First, I will start by setting the stage, introducing the problem setting. I will review some background state-of-the-art work and describe our baseline lyrics to audio alignment. Next, the main part of the talk will be on two different models that extend the baseline with two different sources of music knowledge. And in the last part, I will draw conclusions and we will show some practical applications. Note that the thesis, the sections of today's presentations are divided according to the thesis chapters. First, we will introduce the research objectives, the project context, the problem of tracking lyrics itself, and we will describe why we look at the problem from the particular perspective of knowledge-based tracking and what is new about that approach. The main objective of this work is to create computational models for tracking lyrics, in which we consider music-specific knowledge. Therefore, it makes sense to develop the models in a way for a specific tradition, music tradition or music genre, and take advantage of its particular music principles. That is to say, it is not intended to be broad and generic model applied for any possible type of music. To reduce the complexity of the problem of tracking singing voice in polyphonic music, we will focus on applying it to music with predominant singing voice. And the models will be evaluated on a particular end task, the lyrics to audio alignment, wherein the contribution of the music knowledge compared to a baseline that is not aware of any such knowledge is the important emphasis. Therefore, the perfect alignment is not an end goal. First of all, why study lyrics in singing? Well, singing voice has the unique ability of articulating actual words compared to other music instruments. And this is a quality that I personally find very fascinating. I did my master thesis on speech recognition, and for me it was a natural choice to continue to work with tracking lyrics and singing. There has been various works on singing voice computational research, which are nicely summarized. However, to my surprise, very few of those work tackle the problem of lyrics in sung lyrics, and barely any work is taking advantage of some music-specific knowledge. Oops. Now this project has been carried out in the context of the CompMusic project. And the focus of CompMusic is to create music tradition-aware music information retrieval technologies. Whereas in general, music information retrieval provides tools and algorithms for the description of music data, the majority of algorithms have been designed to tackle music that comes from Western classical music or is based on that music. However, when we apply those approaches to other music traditions, especially the music to the east of Europe, some of these algorithms cannot scale well. Therefore, CompMusic was initiated, and it covers those 5 traditions shown here. Although coming from very different parts of the world, what is common for them is that they are all vocal-centered music traditions. Vocal-centered means that the singing voice is the predominant instrument, and all the other instruments are accompanying it. Therefore, it is rich in some music events such as embellishments, there are different singing registers, which is a very interesting and challenging aspect. Also, those CompMusic traditions have well-grounded music principles because they have been studied throughout a lot of centuries, and because of these reasons, they provide an excellent use case for the goal of this thesis. We will focus on lyrics in 2 of those traditions, Turkish makam and Beijing opera. Let us briefly introduce those. We picked up Ottoman Turkish makam for several reasons. First, it has machine-readable music scores. In fact, it was the only tradition that had music scores when this PhD was started. And music scores are an important source of music knowledge. Next, it had significant musicological literature. And a personal reason for me was that Turkish makam seemed the most familiar tradition. Coming from Bulgaria, I have grown up with the traditional Bulgarian music, and it has been influenced to a big extent by Turkish makam, the music of the Ottoman Empire. In order to avoid overfitting to a particular music tradition, we have evaluated some of the models also on another tradition. And we have chosen Beijing opera, also known as Jingzhu, for several reasons. Mostly because it's challenging. The language of singing Mandarin is challenging and quite different than Turkish. And also because the interpretations of different singers of the same aria from the opera could be quite different. This is because singers follow the example of a given master in the tradition coming from different schools. And in this aspect, it differs from the score that is just a reference. For example, in the duration and variation of the lyric of the vocals and phonemes in general. In this aspect, it's quite different from makam. Next, we will introduce the problem of lyrics to audio alignment. Its goal is to automatically synchronize audio recordings and the written lyrics on different levels. So such levels could be phrases, words, or syllables. In this example, you could see the boundaries of words aligned to the audio signal. State-of-the-art approaches are basically phonetic recognizers that are adopted from speech recognition. And this is important because phonemes and the phoneme identity is the characteristics that human listeners use in order to distinguish between the units of lyrics, the phonemes. There are several applications, most importantly the automatic highlighting of lyrics, for example for karaoke, and automatic thumbnail generation, as well as lyrics-based navigation. And I will give an example of the latter. Not very famous feature of nowadays streaming services is that if you have the lyrics aligned manually by users, you can play it along with the original audio, and you can navigate through the structure of the lyrics by clicking on the corresponding line that is played synchronously. So this is an example of some Turkish pop song in which you can see that you can navigate into the structure.
Endirdin kaşlarını babani, babani mi endirdim? Endirdin kaşlarını, endirdin kaşlarını babani, endirdin kaşlarını babani.
I find it very useful myself for learning songs or for navigating to the structure when I'm trying to learn a new song. And in order to allow the automatic alignment between all the possible songs that you like, it would be great to have automatic alignment, because this is limited only to a couple of songs that has been manually annotated. Next, the most important question is why consider music knowledge when tracking lyrics? First, lyrics have structure organized on different granularity levels. First, lyrics are divided into choruses and verses. Then lyrics have lines within each of those chorus-verse sections. And if we look at a particular line of lyrics, we can note that in most music, there is a fixed number, more or less the same number of musical bars, 2 or 4 bars, for example, which is related to the metrical structure. And then we can observe on all these granularity levels that there are music facets that are related to the structure. For example, if you look at the chords of a popular pop song, we can see that chord changes occur at the first at given syllables. So they are related to the syllables. Then accents of sung syllables are correlated to the accents of melodic line. For example, given syllables are prolonged in order to emphasize melodic accents, and there has been a study that proved that. Also, music is related to the rhythm. So, for example, metric pulsation coincides often with the syllable onsets. Therefore, it makes sense to look at musical knowledge in the form of complementary music context. We define complementary temporal music context, or in short, complementary context, as any music facet that manifests in some events simultaneously to the sung lyrics and have some influence on them. We name it complementary because it complements the timbre of the phonemes, which is the main characteristics. Also, we emphasize that by context we mean these temporal events and not any context that comes outside of the audio, like for example static metadata. For the sake of clearer organization, we have formally divided this context into 3 different levels. On the highest level we have structural sections, and whenever, for example, whenever there is a change of the structural section, there should be a change in the structure of the lyrics. Next, there is given temporal structure within a lyrics line, which means that some syllables are longer, others are shorter. And on a fine level, there is structure of the metrical cycle that influences the changes of some units of lyrics, for example, the syllables. Note that music has repetitive structure compared to speech. Therefore, to summarize, in this thesis, we would like to integrate the knowledge from complementary music context into the phonetic recognizer, because phonetic recognizer is the state-of-the-art approach. And we will do 2 separate models. First is aware of durations of syllables within a lyric line, and the second is aware of the metrical accents within a metrical cycle. So those are the 2 models. And we will focus on the 2 levels because there has been already some work using knowledge from the structure of the written lyrics on the highest level. Next, we proceed to the background of, to review of existing work. And we will focus only on the work that is using the phonetic recognizer approach. In general, the program of lyrics audio alignment consists of typical modules. To start, accompaniment attenuation has the goal to reduce the background instruments, so to reduce the spectral content that has its origin at background instruments because they are essentially noise for the recognizer. Next, a vocal detection has the aim to find regions in which there is only voice compared to instrumental sections. And then features are extracted to represent the acoustics of lyrics. Those features are aligned to a phoneme network by so-called forced alignment because the phoneme transcription network is given in advance. And the phoneme network itself is generated by the given lyrics and using models trained usually on a cappella voice. Note that the accompaniment attenuation and vocal detection steps are not necessarily related to the phonetic recognizer, and they are big research problems on their own, so sometimes they are tackled separately. Here are some seminal works on lyrics audio alignment. Most of them use the male frequency capstral coefficients feature. Other works were trained on speech because there is not enough training material aligned on the phoneme level for singing voice. And then the acoustics of the trained models are adapted to a smaller corpus, which is annotated on the phoneme level singing corpus. A recent approach trained directly on singing voice to make the training procedure less cumbersome, and this resulted in comparable accuracy. However, those work have some limitations, namely that they have been designed and tested on the same language, which usually is English. Therefore, we cannot directly apply any of those models to our case. And also none of them has been, very few of them has been designed to be applicable to another model. Also, none of those approaches is fully reproducible. In fact, we have contacted the authors of those works, and we could reproduce some of the work of Kruspe, which is, however, only for a cappella singing. And none of those approaches, most importantly, considers knowledge of simultaneously occurring music events. Let us look at the evaluation metrics. So if this is annotation of the phonemes, and these are detected regions, so on the word level, for two separate words, we will have incorrectly detected regions. A common metric is the alignment accuracy, which is the percentage of total duration of the segments detected correctly over the total duration of the song. It's a rather strict metric, and usually above 80% is good enough for most applications. Another metric is the average of the absolute error on the boundaries. Next, we will describe our baseline lyrics to audio alignment system. It is based on a phonetic recognizer. We don't consider still music knowledge. The contribution of this chapter is combining existing external modules into a coherent system. And we will refine some of those steps, and we will discuss that. But first of all, let us listen to a demo of the system that we have built. It has been developed for Turkish makam. And while listening, I would like you to see that there are structural sections here, which are denoted by different colors, so that one can click on different sections. And also, we show the alignment on the syllable level. So let's also listen to the music and get familiar with it. Now we clicked on a new section. So we expect to have perfect alignment, which is not exactly the case, but let us look at the way we achieve these final results. So we will discuss some of the steps of the baseline alignment approach. They follow mostly the steps that we described earlier. First, we divided manually the audio recording into segments in this step. Those segments correspond to structural sections from the music score or the music lyrics. And each section that doesn't have lyrics has been discarded. In fact, this replaces the step of vocal detection. We didn't need to do vocal detection separately because each of those sections in the tradition that we use have only predominant voice if it's a section with singing. In order to prove the automatization of this step, we have used an external method that works almost perfectly for finding the structural sections, and we have used this as external knowledge. And in all the experiments in this thesis, we have averaged the results for given segment for the final results, and we have worked on the segment level. In what follows, we will go through the rest of the important steps. First, let's start with the recognizer itself. Phonetic recognizer is in essence a hidden Markov model, and hidden Markov models are suitable for representing lyrics because they can track the time-changing nature of lyrics. Here, the white nodes present hidden variables, and the shaded one observed variables. We have used one state per phoneme compared to most work on speech recognition where there are 3 states per phoneme. Preliminary results show that we have the same accuracy or negligible difference. And we have adopted the MFCC features. In hidden Markov models, we can use this equation in order to detect the most likely hidden sequence, in this case sequence of phonemes, by multiplying those quantities in time. And it consists of two steps, or two important quantities. The first is the transition model, and the second is the observation model. The transition model is learned from training data, usually. We have done the same. We have learned it from speech. And this is, however, not always meaningful, because the transitions between phonemes in speech doesn't represent the same phenomena as the transitions of phonemes in singing. The transition model allows a good opportunity to incorporate some music knowledge. The observation model represents the acoustics of singing given some phoneme classes, and this will be not the focus of this dissertation. We have used the standard Viterbi decoding. This is the equation that Rabiner has formalized, where delta stands for the probability of the most likely sequence ending in state j at a given time k. And know that here, because we have forced alignment, we maximize over the previous delta multiplied by the transition and observation probability only for the current in the previous state, which means current and previous phoneme. Then results are obtained by the timestamps of changes to a new phoneme at deltas that have the maximal value over some time positions here from the most optimal path. In order to reduce the background accompaniment, we have extracted the content of singing voice by 3 steps. First, we have used an algorithm for fundamental frequency estimation in polyphonic music. If we have singing voice, here are the more curved lines and some background instruments, for example here, then this is the result of an algorithm that has been tailored to Turkish makam. Next, we extract the partials at the harmonic partials that are at multiples of the fundamental frequency. And for this, we have applied the harmonic model of Serra. Importantly, the harmonics retain the phoneme identity. So if we extract the harmonics reliably, we can keep the identity of the vowels. And in the third step, we synthesized the extracted vocal harmonic partials using overlap at resynthesis. And this step was done in order to assure the intelligibility of the vocals after the resynthesis by listening. And MFCCs are extracted from this resynthesized signal. Note also that for these lyrics, at some consonants that are unvoiced, there is no resynthesized sound at all because they are unpitched. And last important step is how to train the phoneme models. Although this is not the focus of this study, we exploited 2 different strategies. First, we trained the common Gaussian mixture models with MFCC and their deltas. We trained on Turkish speech, whereas 9 mixtures was optimizing the criteria on the training data. And in order to assure that the models make sense, we have visualized the MFCCs in spectral domain. And in fact, those are the spectral representations of the Gaussian mixtures, where you can see some peaks in spectrum, and this is the phoneme A, vowel A, for which you can clearly see the first 3 Forman frequencies, unlike consonants, which have usually only 1 peak. Another strategy which we tried is multilayer perceptron network. Due to the lack of big training material for Turkish singing, we used the idea of Kruspe to train on a big corpus of a cappella singing in English, whereas we adopted the architecture of 3D players with those number of neurons. And what we did is map each Turkish phoneme to its acoustically closest counter phoneme in English. Well, it was interesting how this approach would work. The data set on which we tested, the baseline and most of the work done in this thesis, was compiled by us because there was no data set for this particular tradition. We selected 13 recordings from the so-called Sharka form, which has verse chorus-like structure. We had music scores with section annotations. So here, for example, each line corresponds to one section. And we created annotations of lyrics phrases within each section. We can see that in a short example. While listening, I would like you to see here the phrases, where each phrase has 2, 1, 3, usually up to 3 words, and this is one whole section. Also note the instrumental accompaniment and the long vocals, and the high degree of vibrato in this music tradition.
Kimseye etmem şikayet, ağlarım ben halime.
A bit different from Western classical music, right? Next, in order to conduct experiments with a cappella singing, we recorded some professional singers in sync with the original recordings for those 13 recordings. And you can hear now together the two versions. Note that we have taken special care to have perfectly matching the syllables of singing. So this is the same excerpt.
Kimseye etmem şikayet.
This is on the a cappella.
Ağlarım ben halime.
This way we could use the same annotations that we did for the instrumental accompaniment. So with this data set, we performed experiments for the baseline system. On this diagram, you could see different phoneme models on the left, on both the a cappella and the multi-instrumental data set. AA stands for accompaniment attenuation, where it was done or not. And you can see the two metrics. Metrics were averaged over all separately aligned segments. And we compared here the Gaussian mixture model and the MLP direct mapping, which stands for mapping from English to Turkish. So the GMM model had rather poor accuracy, which was improved quite substantially by using neural network model. And we believe that although it comes from a different language, the size of the data makes a difference. However, because this model was carried out in the last months of the thesis, we didn't have the time to apply this model to all the experiments, which were initially run with this inferior model. Compared to that, for multi-instrumental sounds, the accuracy was a bit low, however close to the a cappella, which means that the importance of the accompaniment attenuation is significant. And also, this study was published in the Folk Music Analysis Workshop in 2014. Next, we proceed to the core part of this presentation. The first chapter with music context is handling middle level context, where syllable durations within a lyric line serve as a particular type of context on this level. The chapter will be divided into those parts. First, we'll describe the core probabilistic model that is aware of durations, and then we'll show two applications where there are two different sources. One is music score, and another is principles specific to a music tradition. A problem with conventional hidden Markov models is that the distribution of the waiting time is implicitly exponentially decaying. This is because we multiply d times for staying d time in a given phoneme, the probability of staying, and then for each phoneme we will have exponentially decaying distribution, which is essentially the same for the phonemes within a word as well as for the short pauses in between words. However, this doesn't represent well the nature of singing, because vowels are usually longer and the time spent in vowels often depends on some temporal context. One idea how to overcome that is the so-called hidden semi-Markov models, where we have a new variable in the hidden Markov model that accounts for the duration spent in a given phoneme age. When the duration expires, a binary indicator variable is triggered, and then the transition to the next phoneme could happen, and the new phonetic counter is reset. This is described as a dynamic Bayesian network proposed by Murphy. However, in practice, when durations are long, the size of the state space could explode and is not very practical. Another alternative is to incorporate the duration information in the decoding step itself, and this is what we did. So we add an explicit term. In fact, we base this work on the equation proposed by Chen, and this is the explicit term for the probability distribution of the waiting time. Here, big capital stands for product of the individual observation probabilities, which are for the time d spent in the phoneme. And then also note that we have modified this equation so that it takes into account only the previous state because of the forced alignment, and also because of that we don't need the transition probability. Therefore, we maximize over the duration of the previous state and look for the most optimal duration. Using that, we can impose any transition probability. What we did is to apply a normal distribution centered at the reference duration for each phoneme. So, for example, now we will have normal distributions for the phonemes within a syllable, and we will keep the exponential distribution for the pauses in between syllables. We will see how we derive these reference durations in two experiments. First, we derive them from music score. So here the components are essentially the same as in the baseline, except for that part. Taking the musical score, we counted the note values which correspond to a given syllable. So in this example, it would be 8 units for first syllable and 4 units for the second. Then empirically, we set some ways to distribute the duration among the constituent phonemes of each syllable. For example, we fixed given duration for consonants, whereas some special consonants got longer duration, and the rest of the syllable was assigned to vowels. And this way, we could have different sequence of different normal distributions, where we allowed longer, bigger standard deviation for vowels. We conducted experiments with the same data set, with the baseline Gaussian mixture model. We can see on that diagram comparison of the duration-aware model and the baseline model on both data sets. And interestingly, adding those explicit durations increased substantially the accuracy for a cappella case, and this is a system that is ready for industry application because of the good accuracy. However, for multi-instrumental, the results are not so high, still having absolute 10% increase. And we can see why this is so. Here we have ground truth. This is how the baseline would recognize the phonemes, having relatively the same duration for each of them. And then the duration-aware model allowed staying longer at the vowels. This is the vowel E and the vowel E. This work was published in SMC 2015. Similarly, we derived phoneme durations for the other music tradition, Jingzhu, by some specific principles. Before, we should say some words about Jingzhu. It has quite unique singing style, which we will hear in a bit. As we introduce it, is challenging not only because of the singing, but also because of the language. Typical for Mandarin is that there are 2 or more vowels together, which is always a problem for the alignment. And in opera of Beijing, there are 2 role types, or there are more role types, but these are one of the major ones, a female one and a male one. And each of the role types have a different singing style. Lyrics have poetic structure, which means that usually lyrics have the same number of characters. Each character corresponds acoustically to 1 syllable in Mandarin. And usually, within each of those lines, there is this interesting grouping pattern where one dou, a group of 3 or 4 syllables, has the last syllable usually a bit prolonged. Therefore, using this knowledge, we could assign empirically some durations to the last syllables in a dou, where, for example, we set 1/5 of the total duration for the final syllable, and we allowed some bigger standard deviation in order to allow for some irregularities. Then we scaled that to the audio corresponding to 1 segment. And similarly to the previous case, we derived the durations of each constituent phoneme by assigning some empirical rules, putting some fixed duration for consonants. Now let's listen to a demo of alignment done for Jingzhu. We compiled a dataset from 15 arias with the only Dan role type, so it's female singing voice. A cappella material was derived by subtracting from the original audio, an audio that represents the background accompaniment. Therefore, we have tested on a cappella singing, which has almost no artifacts because of this subtraction. And we used a cappella because of the challenging nature of singing. So let's listen. Take note of the long durations and the high-pitched sounds. As you heard, there are some syllables like tian that has 2 vowels, so it's not clear where to put the emphasis on redistributing the phoneme durations. We conducted experiments first with oracle phonemes, which means that in order to capture well in order to assure that alignment can considering phoneme durations is feasible to represent these very long durations in the case of Jingzhu. And these phoneme oracle durations were constructed by considering phoneme annotations, which we considered as an oracle for the acoustic features. So we arrived at close to 100% accuracy, which means that the model is feasible of modeling these durations. I forgot to mention that the acoustic model was trained on singing material for the same tradition, which however was a very small corpus. And we arrived at quite a substantial improvement over the baseline, however not better than Turkish. And one of the important reasons is that we played around with the length of the standard deviation of vowels, where we had optimal results at 2 seconds. This study was published in FMA last year. And next we proceed to the last chapter, which is lyrics-to-audio alignment with fine-level complementary context, where accents within a metrical cycle are an example of context on the lowest level of granularity. This chapter is divided into 2 parts. First, we conducted a study for vocal onset detection using metrical accents, and then using those vocal onsets as a bridge, we did lyrics-to-audio alignment based on the vocal onsets. Sorry. The motivation for doing the first experiment is that vocal onsets co-occur with accents in a metrical cycle, which was shown in a study of sheet music for Turkish makam. And also Turkish makam has well-pronounced metrical accents. Therefore, we conducted a study on material from Turkish makam. And we extended a dynamic Bayesian network representation of the so-called bar pointer model that represents different aspects of the music, where we added a new hidden variable that represents the state of the vocal note. And the goal is to track simultaneously the bar position, the metrical position, and the note state of the vocal. This study, this system of Krebs can be extended. Sorry, the hidden variables can be agglomerated into one variable, which is the Cartesian product of the states of the individual variable, which allows decoding with Viterbi, so that we can use again the approaches of Viterbi decoding that we introduced. And here is the transition probability, which represents the multiple product, which is just the multiple of the individual transition probabilities. We took the tempo and the bar position transition probabilities from the original model, and we derived the phoneme durations, the transitions between note states that are based not only on the previous note, but also on the current bar position. So our contribution is deriving this transition probability, taking a transition model of note states where we have 3 note, attack, stable, and silent. We apply that to polyphonic music with accompaniment. Therefore, we had a non-vocal state at the last stage instead of silent. And we formalized the original model, which was presented recently, where the most important transition is from the non-attack state to the attack state of any of the following possible notes. And this is represented here in that transition. So we modify that by introducing a term that depends on the current bar position. And in fact, what it does is just scales the existing transitions differently at given bar positions. They are scaled in a different way than at other bar positions. So, for example, one way to define this function is to allow some different to scale with this constant multiplied by a function only at metrical positions which correspond to a beat. And whenever there is no beat, there is no scaling. This essentially puts higher probabilities only at beats. Here, the note probability, or the probability of having a note event for singing voice, was derived from literature, where this is an example of one metrical cycle in Turkish makam with 16 positions in the bar, where shaded ones represent positions where there are metric percussive strokes present. Therefore, we multiplied essentially by those probabilities at bar positions, which have beat. The observation model is simply a combination of the two observation model of this approach, of the beat tracking approach, and the note tracking approach. And now, using Viterbi, we decoded. The data set was compiled again especially for this study. We did annotations of beats and vocal onsets to 5 1-minute excerpts from 2-meter types. And let's listen.
Tahammül kalmadı artık. Tahammül kalmadı artık.
Now we'll play that slower, in which I will help you to distinguish the beats so that we can see that the beats really coincide with vocal onsets. Here you can see also the pitch extracted.
Tahammül kalmadı artık.
We conducted 2 experiments. First was with manually annotated beats, and second is with the full-fledged model for simultaneous bar position and vocal onset detection. We evaluated those on 2 rhythmic patterns from Turkish makam and evaluated with precision and recall for the note onsets with tolerance of 50 milliseconds. For the first experiment, we had improvement with annotated onsets. We had also improvement with the automatic detection of bar position. However, this was not so substantial like the improvement with annotations. And similar were the results for the other rhythmic pattern. So compared to the baseline, which was the study of Mauch for transcribing vocal note onsets in a cappella music, we had some promising results. And in fact, this was a study that we conducted just a couple of months ago, and we will present it this year in Izmir, in China. Last part of this presentation will be on onset-aware lyrics-to-audio alignment, where we also have a cappella material. Because it was quite hard, we used the a cappella version of the Ottoman Turkish makam dataset. I'm sorry for that. My skills on presenting with this pointer are not so advanced. So here we have the same steps as in the baseline again. And what is new is deriving the onsets from some rules. Sorry, I mean deriving onset-aware transition rules. So again, we extended the transition model. So let's have a look. This is the standard Viterbi decoding, standard hidden Markov model. What we added is a note state variable, the one that we see from before. And this was based on evidence that syllable boundaries coincide with segments of vocal onsets, and especially the onsets of notes. So we used the onsets in order to change the transition probabilities of phonemes. We define those rules where if a vowel is followed by a consonant, which is not a liquid, then there is chance, and if there is a vocal onset present, there is very big chance that we still stay in the same vowel, because unvoiced consonants cannot bear an onset. And rule 2 is the reverse. If we detect a note onset and we are currently in a phoneme, then we should encourage the transition to the next vowel, and liquids are some special cases that also can bear a note onset. Using those rules, we modify the transition probabilities by, as we introduced, decreasing the transition probabilities in the case of those rules and increasing it in this rule, in rule 2, and leaving it unmodified else. This is so-called variable time transitions, and whenever there are no note onsets present, there will be no change in the transition probability. So here we can use different functions. We did a normal distribution centered at K', which is the position of the closest onset, which means that we redistribute the contribution of the onset so that we can smooth influence from onsets not only on the given frame of the onset. Here is an example. Here there is a consonant followed by a vowel, and here you can see the transition matrix where you have some transitions between following consonants. So by multiplying whenever there is an onset, so there is one here, there is one here, and there is one here, by a Gaussian window, we can see that the transition matrix changes according to time. So from consonant to vowel, the transition probability increases, and vice versa. Note also that whenever there is vowel followed by vowel, for example, the transition probability is not affected. Now we can just replace in the Viterbi decoding the transition probability, and we use the hidden variable for phonemes, which allowed to use the vocal onset detection as a pre-processing step. We use the a cappella lyrics to audio alignment corpus for Turkish makam, and for 6 of the recordings, we annotated the vocal onsets and also the pitch. So this model, in fact, is capable of doing phoneme transcription. Sorry. No, that's not true. So we carried 2 experiments. One was with the manually annotated onsets, so oracle onsets. And we arrived at some improvement over the baseline, that is a hidden Markov model, unaware of onsets. And in the second experiment, we used an external method for detecting vocal onsets, which was developed for flamenco singing. And in fact, it's a full-fledged transcription algorithm. The reason why we didn't use the model of Mauch from before was that this one performed for some reason much better. We expect that the fact that the reason is that it was developed for music that had very similar acoustic accompaniment, and also it was an engineering model which took special attention into difference into the phoneme changes, into the changes of onsets. And therefore, with this model, we can see here that if we increase the recall of onsets, the alignment accuracy also increases. At some point, it saturates. So with this, we also arrived at some small improvement of the baseline. This was published last year at Izmir. Now, what's left is to show some applications and conclude the thesis. So as we heard, here is a demo. Again, now I will play it. Pay attention to the alignment that is not perfect, but however, it is practically usable for final listeners. And this was the model developed as a web application as part of our Dunia platform. This is the model for Turkish makam with durations. And also here we visualized the inverse MFCC features in spectral domain. Another application is a smartphone game, Puzzle, on which I'm working, hopefully after the thesis. And we segment a given audio recording that is recommended by a system into some segments. Each segment is derived by aligning the lyrics to their text. And then we use also other methods, but the alignment is in the core for segmentation. And to conclude, I would like to emphasize that duration-aware model had the biggest contribution compared to a baseline. However, it has the shortcoming that it is dependent on music scores in some cases. Also, we showed that metrical accents can improve the vocal onset detection, and based on onsets, the onset-aware alignment helped to improve phoneme alignment, lyric audio alignment, by defining some transition rules between current and next phonemes. However, the improvement was not very substantial, and we believe that one of the reasons is that the note onsets in Turkish makam are not the best case to create a first model and to evaluate on that, because they are oftenly approached by glides, and it's a bit ill-defined where exactly is the note onset. The important scientific contributions of this thesis is to the conceptualization of the interaction of the phoneme transition rules to some complementary music knowledge, and they are represented as dependencies in the transition probabilities of a dynamic Bayesian network. Since the inference in dynamic Bayesian network is computationally demanding, we proposed several implementations of simplifications for decoding. Mostly we use the Viterbi alignment and reduce the DBN to hidden Markov models. And also, we showed that duration-aware model is beneficial not only for one tradition. Other contributions are listed here. Most importantly, we compiled several data sets that could be used in the future. And we had annotations not only of phonemes, but also of different musical facets that are parallel to phonemes. And we built lyric audio alignment system as part of the web interface called Dunia Web that we just showed, which can be used for enriched music listening and different applications. And also we did implementation of some of the MFCC extracted features. Again, to emphasize that the output of this research is reproducible. We have done Python modules. Because it's a modular, lyric audio alignment is a modular problem, we have done also the architecture of the software in a modular way, so that we believe it could be easily used in the future. It has very few dependencies, only a couple of tools from MTG. And we believe it is the first open reproducible system for automatically aligning lyrics. And also we are working on documenting it well. And in the future, we expect that it will be interesting to combine the duration-aware and the metrical accent-aware models, so the two levels, because they, in a way, complement each other. Whenever there is no note onset, the note onset model is not capable of having any contribution. In these cases, for example, long vowels on the same pitch will can be handled by the duration-aware model. Next, we would like to explore other music facets. For example, we did some experiments with vibrato, and vibrato is related to a big extent to the nature of how long is a vowel held. And we would be extremely happy if we see generalization of the proposed models to other music traditions. In terms of computational models, they are capable to be applied for other traditions. And we believe that the principles that we have studied, the music principles, are not specific for those traditions. Like concepts and durations are typically happening in singing in most traditions. And also, we would like to automate the step of vocal activity detection to replace the structural segmentation. And last but not least, to encourage work on this barely studied topic, for the first time this year in MIRIX, there will be a lyrics audio alignment task, which I personally initiated, and we created a data set, and we will use the evaluation metrics, which are implemented also as part of this thesis. I would like to thank you for your attention and for the patience and interest.